Welcome to this introductory video on parallel computation. Here, you'll get a first look at how computers work together to solve big problems and what makes this field so exciting. In this video, we'll introduce the main ideas behind parallel computing, how big problems are broken down into smaller pieces and solved at the same time using many processors. As challenges in science, engineering, and daily life grow more complex, parallel computation gives us the power to tackle them efficiently, far beyond what a single computer can do. You'll see real-world examples like weather forecasting, medical breakthroughs, artificial intelligence, and the graphics that power your favorite games, all made possible by parallel computing. Throughout this course, you will learn about the basics of parallel computing, explore different computer architectures, and discover how to design and analyze parallel algorithms. By the end of this introduction, you'll understand how teamwork in computing drives modern science and technology. Let's begin our journey into parallel computation together. Welcome to the next part of our course. Let's explore how parallel computers are designed, starting with the big picture. Computer architects use different blueprints to organize how processors work together. One famous way to classify these designs is called Flynn's taxonomy. Flynn's taxonomy sorts computers based on how they handle instructions and data. There are four main types: SISD, SIMD, MISD, and MIMD. Let's break these down. SISD stands for single instruction, single data. This is the classic serial computer, one instruction, one data stream, like a single chef following one recipe. Most everyday computers are SISD. They process one instruction at a time, which works well for simple tasks. Next is SIMD, single instruction, multiple data. Here, one instruction operates on many data points at once. Imagine a coach telling a whole team to do the same exercise together. SIMD is great for tasks like adjusting every pixel in a photo or running the same calculation on lots of data in science and graphics. MIMD, multiple instruction, multiple data, is the most powerful and flexible. Here, many processors run different instructions on different data at the same time, like a team of chefs, each making a different dish for a banquet. Supercomputers use MIMD to solve complex problems, like simulating weather or running large scientific experiments. Now, let's talk about two important ways to split up work: data parallelism and task parallelism. Data parallelism means splitting a big dataset into chunks and processing them at the same time. For example, painting a giant wall with a team, each person gets a section. Task parallelism is when different processors do different jobs at the same time, like building a car where one team works on the engine, another on the body, and another on the interior. Both data and task parallelism help us solve problems faster by dividing the work among processors. Now let's look at how processors share information. There are three main memory architectures: shared memory, distributed memory, and hybrid systems. In shared memory systems, all processors access the same pool of memory, like scientists writing on a giant whiteboard everyone can see. Shared memory is simple and fast for communication, but if too many processors try to write at once, it can cause a traffic jam. Distributed memory systems give each processor its own private memory, like scientists each keeping their own notebook and sending messages to share results. The world's largest supercomputers use distributed memory, connecting thousands of nodes with a high-speed network, like cities linked by highways. Hybrid systems combine both approaches, using shared memory within nodes and distributed memory between nodes for the best of both worlds. To program these systems, we use special tools. For shared memory, programmers use OpenMP. For distributed memory, they use MPI, or Message Passing Interface. Finally, let's look at specialized hardware. Graphics processing units, or GPUs, are designed for massive parallel tasks, like rendering video game graphics or training AI models. GPUs use the SIMD model with thousands of simple cores working together. They are a key part of modern parallel computing. This introduction sets the foundation for your learning journey in parallel computation. In this course, you will dive deeper into each model, architecture, and concept we've discussed, exploring real-world examples and hands-on techniques. Think of this as your roadmap. Step by step, you'll build the skills to master high-performance computing. Get ready for an exciting adventure ahead.